So what I will talk to you about is thermodynamics and a subject that is emerging for the last 20 years, developing relatively fast, stochastic thermodynamics, and specifically how we understand now energy conversion and dissipation. This is joint work with my current PhD student, Olga Movilla, former postdoc Amir Taghvaei, former students and collaborators Rui Fu and Yongxin Chen. So this is a collage that shows Carnot cycles, different contraptions with engines, number of words that come to play during the talk, and this refers to optimal mass transport that somehow connects to all this. If I was there in person and we had more time, I would query, I wouldn't put the names underneath. These are some of the giants that developed the field, and I think it's very important to, and I think most of the audience, I mean, recognize some of the faces. Carnot, Clausius, now this is Gaspar Monge, Gibbs, Boltzmann, Konstantin Karatheodori, Einstein, very, very a significant founder of what we'll be talking to today. If you look at it back in his 1905 paper, some of the ideas can be traced there. Then Claude Shannon, Kantorovich with optimal transport, and Landauer with the connection between information and thermodynamics. So here are some bullet points. So I would like to explain a little bit about the subject, which is at the interface between thermodynamics, the intersection between thermodynamics and stochastic control. It allows you to model thermodynamic systems and talk about energy budgets in a very, very concrete way. There is a serendipitous connection that brings in a whole new dimension to this with optimal mass transport. And I will talk a little bit about optimal mass transport and then utilize the tools that become available to talking about thermodynamic transitions. First, in the context of erasing bits and information, and then harvesting energy. Here I'm going to go fast through this, the first part, just to explain how we picture the interaction of the thermodynamic system with the environment. And then I'll focus a little bit more on anisotropy, because this is how, for example, even biological organisms get the power out of the environment. And then I'll talk a little bit about the concept of an autonomous engine. So this is a standard picture where you think of a thermodynamic system that is contact with a hot heat bath and a cold heat bath, exchanges heat with the environment, and in the process siphons some of this out as usable work. And the story starts with Sadi Carnot, who at the age of 32, published a book out of his own money with some of the ideas that started the field, and then he died shortly after from, I think, the plague. And it came to the desk of Clausius, and the rest is history. The subject took off. The ideas there about the second law, and I'll talk about this, is about reversibility. So you do the transitions very, very slowly so you don't dissipate anything. And of course, out of that comes the efficiency of a steam engine, the golden standard for efficiency, which is the Carnot efficiency. However, there is a problem that the classical theory does not allow you to talk about power, because quasi-static means that you take a long time to do the transition. So if you divide by infinity, you get zero power. There is another conundrum that popped up very early because some of these founders had really good insight. And you probably are familiar with Maxwell's Demon. This is the sort of an imaginary creature that effortlessly closes and opens a door here, allowing particles that have, or molecules that have a lot of kinetic energy to concentrate on one part of a container, and by virtue of this kind of action, decreases the entropy and allows the possibility of generating work out of that. This conundrum drove quite a bit the research for a number of years before it was finally resolved. In what ways work can be used, information can be used to generate work? So there's violations of the second law, and how does this reconcile with our ideas of physical reality? So here is a look ahead, starting backwards from the last thing of how does information translate into work. And the resolution came through this understanding that information processing does not require much work. It's when you erase the information, you clean up the memory that does. So Landauer posed this question of what's the energetic cost of erasing one bit? And he gave an answer that if you have infinite amount of time, then the energetic cost is kBT log 2. T denotes the temperature. So wherever you have a physical device is going to be sitting within some environment that has fluctuations in temperature. KB is the Boltzmann constant that relates unitless quantities to energy. So when you see KB in front, whatever this thing here is a number becomes joules, for example. So where does this come from? This comes from in the following way, that when you have a bit, what does a bit mean? You have a bistable system and sort of like a double well potential, and you have either a 0 or a 1. And the erasure represents the action of taking a bimodal distribution into a unimodal. So, and you do this by changing the potential. And that requires work. And this is, we're going to talk more about that. So this to some degree opened up a little bit the idea of certain models for thermodynamic systems and how they interact with the environment through suitably altering the potential. And then we come in the 90s and we have a number of results on the second law, which is not really cast in stone as we used to think prior to the 90s. There are second law violations. The entropy for a small ensemble can go down as well as up, and it's a large deviations effects. And then we go more into the 2000s, where ideas crystallize into looking at systems at the nanoscale and talking about molecular motors and non-equilibrium thermodynamics. So I'm going to talk more about this. So this work is very recent, and we are working in the same field for some time now. So here is a little schematic that explains the physical models that we're going to see in the next page. So we're talking about colloidal particles, and this is a way to model a movement of mesoscopic systems. So you have a particle here, which sits inside a bath of smaller entities that bounce on it. And this is actually basically even the inside of Einstein's, that you have fluctuation dissipation theory. So fluctuation means that if you leave this particle alone because of the bouncing of the forces around it, it's going to diffuse. And this is Brownian motion. But if you start pulling ahead with a string on this, then this is going to feel a pressure from the particles on one side, and you have the connection between fluctuation and the dissipation if you take action on the particle. So this is all sitting in the background of what we're going to be talking about. So, but this setting here intuition allows us to model thermodynamic system as an ensemble of particles at position X with velocity V that have a mass. There is a potential here, and there is some forces acting, some parameters that you're controlling, and this is your control. There could be some friction, and there is a thermal excitation. T over here represents temperature and can be time varying. Gamma is a friction coefficient, and this is the Einstein formula. And you have the Fokker-Planck equation. Densities are going to be denoted by rho. So that's the Fokker-Planck. Okay, second derivative here and so on. So I don't need to belabor this point in this group. So a typical assumption, and for the most part in this talk, even though we have work done for both overdamped and underdamped dynamics, we will assume that the inertial effects are negligible, and the time scale that we're observing the system is significant compared to this ratio. So if you can approximate then with the first order stochastic differential equation, and this we refer to as an overdamped. So you have dx driven by the potential, and then this is the stochastic excitation. So intuitively, you know, if you look at the previous equation, you just set the mass equal to 0. Okay, and then you derive this. But you know, this is a little bit more subtle to draw the connection. So here the Fokker-Planck equation can be written, it can always be written into this form. And we're going to see this. This is a conservation form, right? So the Fokker-Planck equation has a second derivative. So the second derivative materializes through this, this potential, where it's the logarithm of the rho. So if you think of it, when you take the derivative of the log, you get the gradient of rho divided by rho. So when you plug this in here, you have basically the divergence, and then this rho and that rho cancels, so you get the Laplacian. Okay, if you have not seen this, this is a very nice way of writing the Fokker-Planck equation for suitable velocity field, okay, which is driven by the potential and the density itself. So having this in the background, and again, we focus mostly on overdamped systems, you have an energy associated with an ensemble, and the energy is the integral against the potential of the density. And the first law is that changes in the internal energy have to do with how much work you put into the system and how much heat you put into the system. So the relationship between the two, basically the differential of the energy is the differential of the work and the differential of the heat. That's the first law. These are not perfect differentials in the sense that they don't depend on the state, but depend on the path you take. That's where the bar is from. And when you integrate over time, you get the work that is put into an individual particle. And here is the heat that you put into the individual particle. And this is the Stratonovich notation here. When you average over the ensemble, so I take expectation, you get the curly W and the curly Q. So this thing here is the work that is put into a particular system. So that's the new insight, that you can talk about individual systems, individual particles. And of course, you can think of it as work that you're putting in, or some quantity which is energetic and represents heat. And again, the first law when average looks like this. But the really good insight is that now you can even talk about entropy for a particular system and the particle. So the entropy of a particle is rho T of X, T. So that's the entropy of one particle. And this is the average entropy of the ensemble. So the entropy that we know and love is just average over the ensemble. And there is another quantity that's very important, is the free energy. So the free energy if you haven't seen it, they always explain it as the energy that's available. So if you transition from, it's a function of the state, and if you transition from one thermodynamic state to another, it's the maximum amount of work that you can pull out of it. There's a lot that one can say about this. This is basically the Kullback-Leibler divergence between rho of t and the Boltzmann distribution that corresponds to the potential and the temperature. So the epsilon here corresponds to some potential. So if you take this potential and the t and you freeze them, then you have a Boltzmann distribution. So effectively, the free energy is equal to that, plus some constants. And it always, so yes, I mean, it depends on the transition. So now you can take the time derivative of the free energy. And so if you transition by changing the potential and the density of the ensemble, you can take the derivative and you do basically a budget of what work is drawn out and what heat is being pulled in. The thing that is very, very important to remember, I'm going to go back one slide, is the notion of work. This is the key. So the way you think about this, the work has to do with the change in the potential. So you think of the particle as sitting somewhere inside this potential, and the work you get is through interaction of the particle with a potential which couples it to the outside world. So if you increase the potential and the particle goes up, this captures how much work you have to put in order to do that. If you lower the potential, you get the work that you can get out. So the particles, because they jiggle around, they're pushing against the potential, and it's the interaction of those two things. So this is work and this is heat. The moment you come to terms with this, everything else is easy. And this has been hotly debated in the early days of stochastic thermodynamics about 15 years ago. And it is basically well understood. So anyway, you can do an energy budget, and you take the derivative and you see this term here, which represents work. And then you see the term over here, which has the partial of rho with respect to t. This you can replace from the Fokker-Planck equation, where the V is equal to this expression we saw in the previous slide. When you stare at this, you realize that what you have here is what you have there. And then when you integrate by parts, you end up with a quantity like this, which is absolutely the key. So the V that comes in the Fokker-Planck equation comes over here as a square. Okay? And this we're going to see it again, and this helps us transition to another subject. So, okay, let me say a little bit more about the second law. So here is the formula that we have in the previous slide. And so in general, it's like this. The rate with which the free energy changes has to do with the work you're putting into the system and minus this quantity. So in the overdamped case, it's the V that we saw. In the underdamped case, it's a little bit more complicated. And integrating over time, this quantity, you get the change in the free energy between whatever potential you are, and you have different densities at the beginning and end. The work that you're putting into the system allows an increase in the free energy plus a quantity which naturally we're going to call dissipation, because this is lost if you go through cycles. And this is an improvement on the second law. The second law tells us that the work you put into a system is greater than or equal to the change in the free energy. This is equivalent to saying that the entropy increases. So this now, before we go any further.
Sorry, Tryphon, is this we can think of it as kinetic energy added to the system? Temperature is
potential
rising?
Because right now we're looking at we're looking, again, it is some sort of kinetic energy, but it's really, you have an ensemble inside the potential, and it's overdamped. So they don't have inertial effects. So these particles are sitting against, of course, they are jiggling against the potential by virtue of the fact that have some temperature.
Yes.
Okay.
But the temperature is related to the kinetic energy.
The kinetic, yes. But it's a first order equation that we have. So the gradient dt plus, the square root of 2k bt gamma and so forth dB. So all the kinetic, the excitation comes from the stochastic excitation. Okay?
Yeah.
So let me talk about a serendipitous connection between stochastic thermodynamics, everything I talked to you about, and a problem of the optimal mass transport problem, which has had also a very fast developing phase in the last 20 years in probability theory, control, and many other subjects. The problem of optimal mass transport, so this is a separate chapter here, and I'm just going to make a point, and we'll because it adds a lot in our intuition. So the problem starts with Gaspar Monge, great mathematician, at the time engineer in Napoleon's army, that thought of moving a mass of dirt from one side to another, let's say to build a castle. Actually, he wanted to level the road so that he could carry cannons in Napoleon's army. So, and the problem puzzled mathematicians, including some of the great ones, Abel, for example, for many years. And it came to the 40s, and before Leonid Kantorovich made a very big step, connecting this to linear programming and solving the problem. The Monge formulation, if you haven't seen it, this is enough. You move a mass from here to there, and you would like it. Now, unfortunately, I'm using T here. T is not temperature. T is just a map, right? T is just a map that moves a pebble from X to Y. And Monge asks for the minimum cost. So this is the cost of moving this much mass from X to Y. The original formulation was without the 2 here, but the 2 is very, very nice. And this is what we're going to use. And this is called the Wasserstein 2 metric. It turns out to be a metric between density and distributions and measures, actually. This is a very difficult problem because even when you have, let's say, densities on both ends, so these are absolute continuous, and rho 0 and rho 1 are densities, finding a T is horrendous because there is a very nonlinear relation between everything that's involved. So you want the push forward of mu to be equal to mu. Now, Kantorovich, we're not going to use this, but I think it's educationally very, very important. He looked at it and he said, let me simplify the problem. Let me not try to find the optimal transport, but let me try to find a joint distribution. I can think of mu as the law, let's say one random variable, and this is the law of another random variable, and this is the expected value between the difference of 2 random variables. Square here. And he says, I would like to solve this problem. Then you realize this problem is linear in pi. Pi is a joint distribution, so it's constrained to have the correct marginals. These are linear constraints. So instead of solving Monge's transport problem, you try to solve the problem of finding a joint distribution that has the correct marginals. And that's a linear program, and that's not difficult. Well, it's difficult in infinite dimensions, and Kantorovich developed linear programming specifically for that. And if the marginals have derivatives, so they are absolute continuous, then the joint distribution sits on a very thin set, which is exactly the graph of the transportation map. So there is connection to the Monge-Kantorovich, which is directly staring us up in the face here. I'm not going to talk more about the Kantorovich formulation, but it helps transition to another formulation, which says I ask the question of, okay, so you move from X to Y. But if you take, let's say, 1 second to go there, how is the particle from X to Y? How is it going to move from X to Y? In order to minimize the integral square over the duration, it better be that it has a constant velocity. So I will spare you the details, but this leads us to another formulation of mole transport, which is more of a stochastic control problem. So the same distance between densities is the solution to this problem. This problem says, I want to move from point A to point B all the particles. And the particles at the beginning have this distribution, and at the end have this distribution. I have to respect the continuity equation, and I want to minimize the square of the velocity. So again, it turns out to give you exactly the same value, and it's very easy to see. But this brings a new insight, because this is now an action integral. This thing here is kinetic energy of the particles, and this is over the duration of the path. So this brings us into physics. So W2 is the infimum integral over time of an average kinetic energy. And this originates in a paper by Benamou and Brenier in the late 90s. And there were many contributions, especially by Otto, who realized that the Wasserstein metric gives you a Riemannian metric in the space of distributions. It's almost Riemannian in the sense that I can, that if you have measures, then somehow the tangent space around points, which are measures, is not quite full. But other than that, it's essentially Riemannian. And again, even though we're not going to use it very much, I sketched this here. This is called Autocalculus, not Autocalculus. Densities, and I specialize for densities, so we don't talk about measures. So if you have the space of densities, densities are functions that integrate to 1. The tangent space about a point rho is a perturbation that integrates to 0. Okay. Of course, if the rho is already 0, then you have to be a little bit more careful, but let's not worry about that. Now, you take a perturbation and you can formally identify it with a vector field, which is a gradient of a potential. And you identify it with a vector field. So if you have a density here, a perturbation, which is this, you can identify with a vector field that is pushing the particles that represent the ensemble with the density that you're given to the new perturbation, from rho to rho plus delta. And you do so by minimizing kinetic energy. If you are to minimize kinetic energy, the vector field should be curl-free. So the vector field should be the gradient of a potential. So you identify perturbations to vector fields through the continuity equation. So the perturbation has to be the divergence of rho times the velocity. And then you take the inner product to be the corresponding thing that induces kinetic energy-like quantities. So this is rho times velocity squared. And it turns out that this gives you a Riemannian metric, or almost Riemannian metric, and the Wasserstein is simply the geodesic length. So if you go from some density to another, the Wasserstein distance is actually a geodesic distance. Okay? So that is extremely important insight. The technical details here should not bother us anymore. So let's return to, by the way, if you have any questions you would like to stop me, please do so anytime, if I go fast at any point. So let's return now. This is more for background and intuition. So you have a thermodynamic ensemble that sits inside some potential. So this potential is, so the drift is minus the gradient of the potential, T is the temperature, and the cost of steering via a time varying potential between specified states represents the cost of BT ratio. So you steer from a bimodal to a unimodal, and this insight came to us from Landauer. And how are you going to do that? So whether the potential is allows a bimodal distribution, then you're going to change the potential to ensure that at the end of a cycle, you have reset into the zero. So this represents 0 and this represents 1, 0 and 1. So you lose all memory. And by doing this, the theoretical limit is this much. When there is no restriction of time, the change in the free energy is exactly that. But when there is a limit, you want to do this in finite time, then you can use the things that I explained before, and this becomes the work that you have to put in is the change in the free energy plus something that we can refer to as dissipation. This goes back, this insight started with Orel, Cipher, and where we worked a bit in different contexts on this as well. So this is the key quantity and the improvement on the second law. Here again, I have in this slide a few more things that will not, it's more for context. There are a lot of connections between different insights into violations of the second law, the relevance of information, and so on. We will be only concerned with this that we already discussed. The tradition of the second law is this, and the optimal mass transport bound, when you do it on a finite duration, is this. Now, there were a number of fluctuation theorems that try to restore equality here, because this restores equality between W and delta F by showing exactly how much you lose. There is another very famous equality, which is Zarzynski's equality, which tells you that if you exponentiate and then take the expectation, you restore equality in this way. There are other results, and I will not be able to talk about this, though we have worked on this as well, that tells you how information, so for example, if the particles that you're steering, you're controlling them through some observation process, you may be able to violate the second law and generate work. So there are expressions like this. So again, I will not have a chance to talk that much about this. So let's now stick with the first insight, the OMT bound on the second law, and talk about overdamped particles dynamics in a heat bath, and we'll talk about engines. So the Carnot model of a thermodynamic engine represents to a cyclic operation on an ensemble. So here's the ensemble. And here it sits happily inside this potential. Then we manipulate the potential, so we open it up. The way you can picture it is as if you have a cylinder and you allow the piston to move out. Because the particles are pushing against the potential during this part of the cycle, you can get work out. Then you can instantaneously or very fast transition from this potential to that potential without altering the density. And the entropy remains the same of the ensemble, but you can get a little bit more work out. And then you start going in reverse. You put work into the system to bring it back into the density that you began. So this is, I'm going to explain this. So you have isothermal transitions when you go like this, because the system is in contact with a hot heat bath, and here with a cold heat bath. So you switch the temperature. And then you have adiabatic transitions horizontally, and that is the Carnot cycle. This is the abstraction of the Carnot cycle. And you do it in such a way so that you start with some density, you end up with another one. Here, the transition is fast, so this is not affected. But then this potential is in agreement with that. So you see, when you open up the potential and you do it in finite time, the density is going to trail the Boltzmann distribution for the instantaneous value of the potential, right? It's going to trail it. So, so when you reach this point here, you could switch the potential to be the potential which is like the logarithm of rho, and then start compressing again. And then you can do the budgets for the cycle. So again, this is the energy budget that we discussed before. So you take the derivative of the free energy. If you go through a cycle, the free energy comes back to the beginning. And in the meantime, you can see how much work and how much losses you get. And through the isothermal expansion, you have that the work that you put into the system is the dissipation. The dissipation has to do with the distance between the endpoint distributions and the change in the free energy. And there is some heat that enters into the system, and then you compute that. The adiabatic, again, I'm just repeating myself, is an abrupt change in the T. The rho stays put, and then you gain some work or you lose some work depending on your choice, but there's no heat that flows into the system. So when you put all of this together through the cycle, and assuming optimality, optimality has to do with the path going from the beginning to the end density. So if, for example, you're sitting inside a quadratic potential and you have Gaussian distributions, it's relatively easy. You can get quantify the work extracted. And this has to do with the difference in the temperatures and the change in the entropy. And then this represents losses. And then the heat drawn while you are in contact with 2H, again, you can compute that. This is all straightforward computations. And then now you can answer any question you like. For instance, you can say, what's the efficiency? So the efficiency is the work that you get out over the heat that you suck in when you are in contact with a hot heat bath. And in the limit, when the time that it takes for you to do the transitions goes to infinity, the dissipation disappears and you get the Carnot efficiency. This is a celebrated Carnot efficiency. Otherwise, you get losses and you get less. And then you can also talk about power. You look at how much work you do over the time it takes you to go through. Remember that T1 and T3 in the cycle, I'm skipping back now here. So the cycle takes T1 seconds to go here, T3 seconds to go there. The T2 and the T4 are basically instantaneous. It's an idealization. Okay? So when you do this, then you can compute the power. And then you can get a number of interesting problems. You fix, for example, temperatures, you optimize over the cycle, that's easy, and optimize over different rows under different connections. And there are several results and several approaches on this in the literature for different situations. I'm going to talk on a slightly very similar thing, which I think will give you, because some of the formulas become complicated, but I just have a couple of slides on this type of engines for a very interesting situation that is quite physical. So you can think that in many cases, and we're going to talk about this, there's no one that is going to switch you between the cold and the hot heat bath. Either there is a fluctuation in the temperature, or there is something else that somehow you're in contact with both heat baths at the same time. So there is a cold heat bath and a hot heat bath at the same time. For example, the sun warms this side of my body, and on the other side, I feel the cold of the room. So I'm going to talk more about that after this. But there are some times that, the sun rises, the sun goes down, and you have a periodic temperature. And you're asking the question, is it possible to draw power out of it? And the answer is yes. So you can do that, again, keeping the budgets for how much heat you can draw, how much, by changing suitably the potential. And you can see that the maximum power that you can get by suitable choice of the thermodynamic potential has to do with the variation in the temperature. So for example, if you switch abruptly between the two, T hot and T cold, this is a bound in the power you can draw in the Carnot cycle. The sigma mean here is a little bit more technical and has to do with the shape of the density. Like, for example, how much resolution you have with the potential to controlling the position of the particles. And then this is the efficiency at maximal power. And for underdamped systems, you get very similar quantities. And then you get, interestingly, you get square root of the temperature, which is something that one would like to ponder about. So I don't have a physical intuition on this. But you get some very interesting formulas which agree in the limit with known insights. So, and with that, I'm going to go into the last thing, the last chapter that I would like to talk about on engines. And this is, so the rest of the talk is basically to explain to you this picture and something called Brownian gyrator. So this is a different type of engine. And I claim that to some degree, again, this is a little bit of going on a limb, that most of biological organisms, to some degree, draw power out of anisotropy, out of, maybe anisotropy is not the right word for it, but you have a gradient of some potential. The potential is not constant. It's not, you have a gradient, for example, a gradient of the heat. So this side is hot, this side is cold, and I'm in contact with both of them, okay? So I would like to explain how you can draw power and energy out of this. So imagine that you have a mass that is suspended by two springs. So you have one spring here, right? And you have another set of springs here. And then, it's a second order system. You write down the equations of motion. And if I perturb it, it's going to do some complicated movement around there. Now, if I allow excitation in these two directions, so someone jiggles with a spring here, and you have some excitation and some other excitation in the other direction. What happens is, because if I have excitation in two directions that are not lined up with the springs, then what happens is you end up having a circular motion. So on the average, the particles start moving about. So basically what you have is you have a second order system. So here you have x dt plus some b dw. So even if the b here is diagonal, you have a stationary distribution, but it's not equilibrium. So in other words, the particles sit inside a stationary distribution, but there's a probability current that goes around. it's that probability current that you take advantage of. This probability current basically tells you that if this is the potential that the particles are sitting in, the stationary distribution is a little bit off with respect to the potential. So the particles are pushing against a side of the potential and they're going away on the other side. So if, for example, here I'm here and I turn the potential, then I can get work out. So this is what we're going to take advantage of. This is a physical incarnation of it. So if you put in a resistor here, which is a hot resistor, you get fluctuations which are Nyquist-Johnson noise, and this is a cold resistor. If you have some capacitors and the capacitors are chosen suitably, you're going to get circulating currents. So this was already observed in a couple of publications. It was proposed first by Fillinger and Ryman, and there has been some analysis of this in terms of the torque that's being applied. And we work out completely the limits to how much energy and somewhat much power and efficiency you can draw out of such an engine. And then we're going to have I'm going to have a discussion on the physical incarnation of this into an autonomous engine. And this basically will conclude my talk. So this is the Brownian gyrator. This is the model. You have a potential that couples these 2 degrees of freedom. The first degree of freedom is excited in some temperature, and the other has a different temperature. So there is the hot direction, the cold direction. And you have a quadratic potential. So K is the quadratic potential, the matrix of the potential. So sigma denotes the covariance of the state. T now, which is a temperature, is a tensor, so it's a matrix. And the covariance obeys, of course, the Lyapunov equation. Now, this Lyapunov equation, typically we think of K as our control and we solve for sigma. But we can do it the other way around. So if I specify the sigma, I can find the K that corresponds to this equation. And I can do it right here. It has this somewhat complicated expression. If you haven't seen it, it's a very interesting. So this is just the differential Lyapunov equation that we teach in graduate level courses. And this is so if I move the T on the other side and I have K sigma sigma K, right? So if I have, let's say, in the scalar case, I have -2 sigma K is equal to something. So the K is going to be the something divided by -2 sigma. So the way you do this with matrices is, this is like a matrix division of sorts, okay? But you do it because these are non-commutative objects. So why we do this is because we want to simplify our thinking and trace trajectories on the thermodynamic manifold. The thermodynamic manifold will represent the density of the particles. So the densities are going to be Gaussian, so we're going to be keeping track of them with a sigma. Now the sigma is going to be analyzed into some rotational matrix by some theta, and the eigenvalues of the covariance. So the eigenvalues of the covariance, we choose to trace path where the entropy stays constant. So we choose, just for simplicity, the determinant of this matrix here to be constant. It turns out this is extremely interesting because this determinant becomes a characteristic length that enters in certain formulas. So you will see it in some places, but that's not so important right now. What I would like to underscore is that the sigma now, because the determinant is constant, can be characterized by 2 quantities, the theta and the ellipticity sort of the level sets. And that we call R. It's the logarithm of the two quantities here. And then moreover, we replace the theta with a phi, which is twice that. The moment we do this, we map every sigma, every covariance into a Euclidean plane. And these are going to be polar coordinates. So the state of our manifold is going to be a point in a Euclidean plane. And these are the level sets of a quadratic form with matrix sigma. So here you see the ellipticity of it, and the R represents, R represents the ellipticity of it. So the further out you go, it's more elliptic. In the center, you have a circle, okay? And then the phi tells you how it tilts relative to the axis where you get the stochastic excitation. So we're going to trace cycles inside this thermodynamic manifold. Ideally, if you go along this line, this is what happens to the covariance. It just becomes from being oblique like this, becomes like that, then you turn it around, and then again, you go like this. But we can trace other cycles. And we can do the budget through the cycles. So just in order, let me skip some of the computations. So the thing that I was saying before, these are exactly the cycles. And the ideal cycle that I showed you before was something like this, you know. Okay, so I'm going to explain you a little bit the situation here. Right, remember, the sigma is the covariance of the ensemble, and it represents the density, how they sit relative to some potential. And the potential I can decide, I can move the potential so that I can steer the density. So I'm not worried about that, because the potential can be computed depending on how fast I want to steer my density, okay? So as long as I prescribe a path on the thermodynamic manifold, I know what to do. So now I'm doing the budget, the energy budget. I have the energy, which is the potential energy. The potential energy is the trace of the control times the covariance. We take derivatives, and then we have heat and work, and we can work it out. So the heat that is drawn can be split into two pieces. One of them is quasi-static, and one has to do with dissipation. And it's interesting, one of them depends on sigma dot, and the other depends on sigma dot squared. So that this part here, if you do it very, very slowly, because it depends on sigma dot squared, goes to 0. And this represents, this represents losses when you do things in finite time, whereas this quasi-static work is transformed into work. So then we change coordinates, and we play a little bit with how conveniently you can do the computations and tracing what's happening. And so here, this is the thermodynamic manifold. And what you see is that so any path here represents a path of the sigmas, which again is represented by a rho and a phi. So in polar coordinates, every point represents a covariance. And when I trace anything, and I trace a closed cycle here, I get some quasi-static work, which is given by this expression. And this, it becomes an area integral of a suitable density inside. And then the dissipation in the next slide, the dissipation, which is this, becomes a dissipative work that will be lost. So if you work it out, this can be written in this way with alpha, the derivative of r and phi. So it is a velocity field. And there is a Riemannian metric here, which quantifies the losses. So this is basically length. And the dissipation is greater or equal to that. And it's equal to that if you traverse the path with constant velocity. So if we traverse cycles with constant velocity, you basically get the length of it. That's dissipation. The area here relates to work that you get out. And then you end up with an isoperimetric problem. So here, this is area. This is length. And the work that you get out, again, it relates to the area minus the length squared. And the length relates to the dissipation. So the maximum work out, you maximize the A over some fixed length, for example. And these are isoperimetric curves. Now, you can talk about efficiency. So you can say they work out over the quasi-static work, the work that has the potential, it's the heat you're drawn in, and you can get expressions for that. And you can show that, for example, area over length square is greater than 1 over 8 pi. You can talk about the curvature of the thermodynamic manifold, and you can use properties of that in order to get the bounds on the maximum achievable efficiency. And the maximum achievable efficiency turned out to be basically a circular path, very fast around a certain point. So it's sort of like a limit. It's an idealized situation, and it reaches this this bound. So now these are, as I said, these are isoperimetric curves for a fixed mu. The mu is some parameter that comes into the equation and amounts to choosing a length, or amounts to choosing some characteristic time for traversing the cycle over your choice of cycle. So if you choose to go around the cycle of the engine in, let's say, 5 minutes, you have to compute something that has to do with the time constants of the system, and the ratio of those two things gives you which is optimal in the sense of getting the maximum power out or the maximum efficiency out. So now let me go a little bit more. I think I'm going to take another 4 minutes, 5 minutes. Would that be okay? How much time do I have? Because we started late.
Yeah. The time is very flexible. So
okay.
Yeah.
All right, then we can talk after this. Yes.
Yeah.
So again, well, let's go back to this example here, which is this Brownian gyrator. You have the two heat baths, which are Nyquist-Johnson noises. You have some potential, and Q is some charges in the various capacitors. And the potential basically is the energy inside the capacitors, which they have some capacitance. And the capacitance looks like this. So you have one that is on this side, another capacitor on that side. I think I had it the other way. Okay, I had it right. And then there is a coupling capacitor here, and all of them together play a role. So this is a positive quantity. It's a symmetric matrix. So how are we going to do an engine out of this? The idea is to change the capacitors. So for example, we could put a rotating an inertial wheel in here in the middle and link those to the electric material in the capacitor. So as this rotates, it pushes and pulls in and out the electric material. So intuitively, when the voltage here is increasing, then it sucks in the dielectric material, which allows the torque to be used to generate a torque. And if you time it right and you put this point here at the right proper place, we can actually generate limit cycles for this engine. So it all has to do with how the position of those things relative to the different values of the capacitances. So you have theta is the angle of the wheel here in the middle. You have some inertia of the wheel. You have some friction here of the wheel, which will be coupling to an external load. The C is 2 periodic. And then you write the equations of motions. So Q here is a vector. It incorporates both degrees of freedom. This is the Brownian gyrator. And this is the mechanical part. The mechanical part is the angle of the wheel. This is the angular momentum, the angular velocity, angular velocity. I is the inertia of the wheel. And then you have a torque generated by the charges and the capacitance. And this is the work that comes out through coupling to some external load. So you can assume this thing to be, the gamma to be constant. And then we have the kinetic, the change in the kinetic energy of the wheel will have to do with the work that you put out and the work that you put in from the capacitances. So this is sort of a balancing of the work from the different sources. And assuming that the electrical time constant is much smaller than the mechanical time constant, we can solve, sigma is some solution to the Lyapunov equation, omega and theta, so are the variables of the mechanical part of the system. But basically, if we look at, we can think of theta as an independent variable. You see here, I'm skipping back. We can think of theta as an independent variable and write the second equation as a function of theta. And then we basically have this this equation modeling sort of the total system. And we can draw the phase portrait and show that, again, there's a lot of detail here, but it turns out that there is a stable periodic orbit. So the theta increases in this direction and the omega, right. So this direction is omega, this is theta, and this is omega. And you have a stable periodic cycle. So intuitively, the dynamics of the system amount to the dynamics of a pendulum. So this is the theta, and omega is the theta dot, where a torque is applied to this, a torque. The torque is not constant, but on the average, it produces positive torque if you rotate in this direction. So you can think of this as simply a positive torque. If it's a positive torque, you have a stable equilibrium here. But if you raise the pendulum up here, then the torque will produce a lot of work by the time you reach this point, and that will be enough to overcome the external load and bring you back to this point, and so on. So this is basically a phase plot as we would do in a graduate level class. It's quite subtle. There are lots of, these things here are isocliness of a vector field. So I can talk more about this, but I don't think that's, the point is that you can establish the existence of a periodic limit cycle from which you can get work out of it. So the work that comes in, there's some dissipation and some work that can be drawn out. So as a recap, I wanted to say that stochastic thermodynamics brings at least a certain regime of studying thermodynamic systems, mesoscopic systems, within the realm of stochastic control, and we have a lot of tools there and a lot of insight, and it allows us to do analysis for how engines or other processes dissipate or transform energy from one form to another. I explained sort of the inside by discussing a little bit Carnot cycles, then gave a little bit of intuition of how formulas for power and efficiency relate to the temperature and the changes of that. Then again, the second law and BT erasure gives us further insight. And then what I refer to as anisotropic fluctuations is really non-equilibrium steady states. So you have a kind of a steady state. It's not a steady state because things are moving and you could change the potential. And then you can draw power out of this. And then this relates to a isoperimetric problem where the work that you get out has to do with the area and the length that you're traversing. So, and with that, I would like to close and say that there are many, many interesting, I haven't talked to you about updates of the second law where you have an observation process and the information gives you some advantage. But of course, the information comes hand in hand with some processing which dissipates energy due to the mechanism of erasure. So there are a lot of directions still to be pursued, but I would think that the nice directions that we are pursuing is generating ideas that relate to the viability and efficiency of nano engines, and probably in the near future, trying to understand whether biological processes that tap on anisotropy and gradients of chemical and thermal potentials have actually, due to, I don't know, evolution, maybe evolved to be optimal or very close to optimal. So for now, we are really exploring bounds and issues of robustness, whether large deviations, the probability that an engine will come to a standstill is also something that needs to be understood more properly. And I have over here the word circuit theory. So I'm envisioning also that thermodynamic transitions in finite time and with the tools that are right now exist will allow us to have a version of circuit theory where we connect many such components and have a simple way of manipulating and saying, for example, a transformer of energy of a certain type to another type, and speak at a sort of a higher level when we think of not just a simple engine, but many such components being connected together. So I think it's a very exciting area. And for now, we're having fun exploring the different limits to what can be done in ideal situations, admittedly. So with that, I would like to end here and thank my team, Olga, Amir, Rui, and Yongxin. These are absolutely brilliant colleagues and students, and I've had a lot of fun exploring this subject. So thank you for your attention. And yeah, I don't have any, here. Thank you for your attention. And I would like to acknowledge some support by NSF and AFOSR.
Thank you very much for the fascinating talk. So I think the floor is open for questions and discussions. Maybe I could start with a very